have.
Are we ready? You ready?
Sure.
Okay. So for today's Colloquium, it's a pleasure to have Jenny Hoffman from Harvard. Yesterday we heard about topological materials from the theoretical point of view. Today we're going to hear about how to image them experimentally. Jenny got a degree at Harvard, her bachelor's degree at Harvard. She then got her PhD at Berkeley, and she postdoced at Stanford. Then she went back as an assistant professor at Harvard, rose through the ranks, left for a year to UBC, and now she's back. She's worked on superconductors, on charge density weights, charge ordering, all sorts of electronic interactions with materials, particularly on imaging them. And when you read her Wikipedia page, after it finishes with all this, there's a little section that also says that she's an ultra-marathon runner. And the thing that absolutely blew me away is in 24 hours, she ran 142 miles. Anyway, she's not going to talk about that. I don't think.
Actually.
Yeah, actually, okay. Let me get the lights. That I could never do.
Well, thank you so much for the kind introduction, and thank you so much for the invitation. And I really appreciate your persistence, Paul, because I've been wanting to visit NYU for a while, and various circumstances contrived to make it difficult, but I'm really happy to be here today. It's always magical to pop out of the subway in New York City, so thank you so much. Okay, so I'm going to talk about imaging topological materials, and this talk has 3 parts, and I may or may not get through all of them, and that's okay. It's a modular talk, and I really hope in this kind of really lovely, informal setting for a colloquium that you'll feel free to interrupt me, and if I don't finish, so be it. That's fine. So why are you all here? I heard that there's food afterwards, so I suspect that half of you may be here for that reason. And the other half of you may be here to play a game of seminar bingo or get credit for some talk. But more generally speaking, why are we all here? We're all here because at some point in our lives we were inspired by some images like this of intergalactic space. Or I guess this is the center of the Milky Way. Or we were inspired by images like this of subatomic particles. And my story maybe started there with the astronomy or the subatomic particles, but it was a little bit of a Goldilocks story. The astronomy turned out to be too big, the subatomic particles turned out to be too small, and I ended up somewhere in the middle with atoms. And I want to make the case for why atoms, why this middle ground is really something to be passionate about for a long time. So I took this image. This is actually an image I took in my first year of graduate school, and I framed it and I put it on my wall. I thought it was so beautiful. This is the image of atoms on the surface of a high-temperature superconductor called BISCO. So what's the case for materials, for atoms, for quantum materials? So the case is that it's closed-loop physics, and let me tell you what I mean. If we look at astronomy or we look at subatomic particles, the trajectory goes something like we observe a phenomenon, it's a really beautiful phenomenon, we discover something new, and we spend a lot of time writing down beautiful mathematical equations to understand that phenomenon. On the other hand, solid state physics, this length scale of atoms, which is in between these 2 length scales, it's solid state physics is another name for it. So this is Kittel's book, which is kind of the Bible of solid-state physics. And when I was a graduate student, I had the luck to travel to a conference in China, and I took the opportunity to pick up solution manuals to all my favorite textbooks. And I picked up the solution manual to this one. And you may notice, if you look carefully, that there was actually a typo in the title of this solution manual, which I thought was very funny because solid-state physics does, in fact, have a reputation for being somewhat dirtier than the beauty of astronomy or subatomic particles. The equations are messier. We deal with 10 to the 23 electrons, and one can't write down a closed-form equation for everything that's going on in these materials. But they're fascinating nonetheless, and the reason is that not only can we observe and understand these materials, but we can use our understanding to design new materials, and then we have tools to build those materials. So in fact, we're doing closed-loop physics. And this is an area of physics where, in addition to understanding the beauty of the world, we can actually take steps to influence the future of the world by creating new materials. So how do we make materials? In my lab, we have a molecular beam epitaxy system. And do I have a point? You know what I'm going to do? I'm going to turn the pointer on the PowerPoint. Sorry. Here we go. Laser pointer. So in my lab, we have a molecular beam epitaxy system, and we grow two-dimensional films of materials out of elements in the periodic table, which we essentially treat like our Lego building blocks. We transfer those materials through ultra-high vacuum down into a scanning tunneling microscope system. And how do we image those materials? We have several of these scanning tunneling microscope or force microscope systems where we scan a tip, a functional tip, and 1 pixel at a time we measure some property of the material. And so for today's talk, I'm going to be focusing particularly on the topological materials, although we have a lot of work, as Paul said, in superconductivity, charge density wave materials, quasi one-dimensional materials, magnetic materials, phase change materials, etc. So these microscope tools are really powerful and allow us to look at a variety of different materials. And again, always our theme, though, is trying to look at materials that might have some impact, and materials where ultimately we can make changes and design new materials to influence the world in the long run. So the outline for my talk is I'm going to start with an introduction to topological materials. And I know you got an introduction yesterday that was theoretical and mathematical, and I'm going to give you an introduction that is cartoony and intuitive, to me at least, and I hope that it's helpful, with a brief introduction to band structure. And then I'm going to talk about what topological materials could be good for. So one application is spintronics, so I'll talk about how we can measure some of the metrics that would make a good spintronic material. And then I will move into strongly correlated topological materials, and finally a few slides at the end on something very new data coming in a couple days ago from one of the undergraduates in my lab on topological metamaterials. So what is a topological insulator? Topological insulator is kind of like a chocolate bar. It's a insulator wrapped in a conductor, but the difference between a topological insulator and a chocolate bar is that no matter how hard you try to open the chocolate bar, you can't remove the conducting surface state. And that's because the conducting surface state is topologically protected. So at the end of the day, you're sad because your yummy chocolate bar still has this protective conducting surface state on it. And how do we understand that? We have to take a brief dive into band structure. So what is band structure? So a single atom has quantized energy levels. And if you put a bunch of atoms together, you can no longer have all of your electrons living in a single energy level because of the Pauli exclusion principle. So all of those 10 to the 23 electrons spread into an energy band. And you can plot those energies as a function of momentum. This is called the band structure. It's the dispersion relation of the electrons. And you can ask, well, how many electrons are actually in the material? So far, these are just the states that are available for electrons to sit in. But in any particular material, there are a fixed number of electrons, and the electrons fill up the available states to a certain highest energy, and that highest energy is called the Fermi level. And when the Fermi level sits in the middle of a band, then it takes an infinitesimal amount of energy to excite an electron and get it moving in a particular direction or conduct electricity, so that's a metal. If the Fermi level sits in the gap between bands, then it takes a finite amount of energy to excite an electron and get it moving with a net momentum in a direction. So it takes a finite amount of energy to conduct electricity, and that is an insulator. So we're going to focus in the talk primarily on insulators. And so if I zoom in on this insulating gap here, and I look at the P states and the S states, I have an energy level diagram that looks something like this. So my P states are sitting below, here's my 2 P states and my 3 S state. And in a material, there's always a spin-orbit coupling. The electron feels the effective magnetic field from the electric field of the nucleus, which splits the 3 degenerate p orbitals and opens an energy gap between them. And if you then take a material that has the Fermi level within this gap, so this is an insulator, and this is the boundary of the insulator to the outside world, vacuum, and here's the Fermi level sitting in the middle of the gap. Now if I look at this spin-orbit coupling here, and I turn up the spin-orbit coupling, suppose I go to a heavier element so that spin-orbit coupling increases, then the splitting between the p orbitals here is going to increase, and what's that going to do? if I increase it enough, that p orbital is going to pop above the s orbital. And so now what's happened inside the material is that the bands have inverted, whereas the outside has not changed. The outside of the material is still in a topologically trivial state, whereas the inside of the material, there's a topological twist in the bands of the material. And that topological twist, inside versus outside, has to be somehow untwisted at the boundary of the material. And the only way that this twisted gap can be untwisted is to, at the edge of the material, break the gap. So to untwist the gap, it has to be broken at the edge. And what is a broken gap? A broken gap is filled with states. And so at the edge of the material, we have conducting metallic states that pass through the Fermi level of the material. So this is what makes our chocolate bar uneatable, that no matter what we do, at the edge, there's always going to be a conducting surface state. Even if we break it, it will immediately have a conducting surface state on the new boundary of the material because of this topological requirement. So this was theoretically predicted, as you saw yesterday, by Professor Kane and others, and Professor Zhang as well, who unfortunately passed away 2 weeks ago. And so I want to pay tribute to the amazing work that he's done in this field, which it's hard to even put together a talk like this without thinking of him on every slide. But I also want to credit Professor Ray, who was one of the key people in the experimental discovery of these materials. So in his PhD work at Princeton, he was among the first to actually use angle resolved photoemission and measure the dispersion relation, the energy versus momentum relationship of the metallic surface states that live on the boundary of the material. And these surface states take the form of a Dirac cone, and they're actually spin-polarized. So the states on one side of the Dirac cone have one spin orientation, while the states on the other side of the Dirac cone have the other orientation. So why are they spin-polarized? I'm going to tell you again in a sort of phenomenological Hamiltonian here. So let's say we have a gap in the density of states, and the Fermi level is sitting in the gap. So these are the bulk density of states of the material. This is a bulk gap. Now, the surface of a material is always different from the bulk. The atoms have different coordination. The electrons feel a different environment on one side than on the other side. So typically, there is some kind of electronic structure at the surface that's different in the bulk of the material. So the simplest way that you could have a surface state is just to assume, let's assume we have a two-dimensional free electron gas at the surface. So the dispersion of the free electron gas is just 1/2 mv squared. So here's our Hamiltonian, just a parabola, quadratic in momentum. So that's the kind of simplest manifestation of a surface state. Now, the surface breaks the inversion symmetry because out is different than in. And so necessarily there's some electric field at the surface that points out or in. And because of this electric field, which is there just because of the broken inversion symmetry, any electrons that are moving in that field will, by relativity, see that electric field as a B field. And so electrons at the surface of a material will feel the B field and will exhibit spin-orbit coupling. So here's the effective B field from the electron's relativistic view of the symmetry-breaking E field, dotted with a spin. So we get this extra term in the Hamiltonian, the spin-orbit coupling term, otherwise known as the Rashba spin-orbit coupling term at the surface. And so if we add this spin-orbit coupling term to our original simple quadratic kinetic energy term, then we get a Hamiltonian that has kinetic energy, a spin-orbit coupling term. But this still, and the spin-orbit coupling term splits the spin-up band from the spin-down band. So now instead of one parabola, we have two parabolas with different spins. But this isn't enough to make a topological material, because if we say dope the material, if we put more electrons in or take more electrons out, then this Fermi level can move up or down. The filling of these states will change if we put more electrons in or take more electrons out. So this surface state is not topologically protected, the one that I've drawn here phenomenologically, because it's not guaranteed to go through the Fermi level. I could move the Fermi level down, and there would be no conducting surface states, nothing crossing the Fermi level. So although these are spin-split surface states, they're not necessarily topological. So we can add a term to the Hamiltonian that at least phenomenologically captures the topological nature of these states. And if we add in a term here, then at least phenomenologically we can see that that has the effect of bending the outside of these states down so that they touch the valence band. And now, no matter where we put the Fermi level, anywhere within this bulk gap, it passes through the surface states. And so no matter what we do in this case, these surface states are going to be there and they're going to be conducting. So this looks phenomenologically like a topological insulator. There's one more term that we can add that has to do with the crystal symmetry. And so the simplest description of a topological material surface state is this Hamiltonian here, with an offset term, an effective mass term, a spin-orbit coupling term, and a couple of other phenomenological terms that bend the bands down and match the crystal symmetry. Okay, so this is a topological material, but what is it good for? So I want you to focus on the spin-orbit coupling term here. This spin-orbit coupling term is the one that splits the bands and tells me that a spin, that if I'm here, if I'm sitting at this energy and I have a momentum going in this direction, I must have a spin down. But if I'm sitting at the same energy and I have a momentum going in this direction, I must have a spin up. So the spin of the material is, the spin of the electrons is linked to the direction of the electrons. And that means that these materials can be employed for spintronics. If we can send a current in one direction or the other, then we know what spin that current must carry. And so a topological material is hypothetically a really good material to generate spin currents, to allow computing with the information carried by the spin of the electron rather than the charge of electron. Okay, so what are some metrics for what would make a good topological material for a spintronics application? So I'm going to give you some examples on the material antimony. So antimony is a humble element, but it turns out it's a topological element, and this also was shown by Professor Ray in his PhD in 2009, I believe, that antimony by itself as an element is topological, has a topological surface state.
Okay, can I, going back one?
Yeah.
I thought you were saying that if you
Please interrupt, yeah.
you have the spin, you know, if it's going this way versus this way, you can adjust the spin, and which is clear. And then, but the spintronics, this kind of trying to compute with by manipulating spin as opposed to current. I understand that part, but it sounds like these two, in this situation, it sounds like you're getting the spin by running current. So how did?
Yeah. So the idea is that the spin current is protected, and what you would do is you would put this adjacent to some kind of magnetic material. And so you would use this as a generator of spin current, but probably the information bits would be in an adjacent ferromagnetic material. And the beauty of these materials is that just by sending a current, you know you can generate the spins that you want. And then those will couple into the adjacent ferromagnetic layer. Did I answer your question? Or
Yeah, because otherwise it just seemed like you're still moving current around.
Yeah, right.
Okay.
Yeah. Okay, so what are some metrics of importance for using these for spintronics? Well, there's that term in the Hamiltonian that actually tells us how strongly the spins are coupled to the momentum direction. So it tells us how split those bands are. So that was just one of the terms in the Hamiltonian. Another important metric is the mean free path. If you're going to send a current through this material and expect that your spin information is going to get from point A to point B, then you want this electron, the spin information, to have a long mean free path. You want to reduce the scattering. And finally, what can mess up your spin current is if you have a magnetic defect in the material. Because if you have a magnetic defect, then your electron can scatter off the magnetic defect and flip its spin. And the susceptibility to external magnetic field or magnetic defects is captured in the G factor. So ideally, you would like a strong spin-orbit coupling, a long mean free path, and a small G factor. So how can we measure these things in the material? Well, to make nanoscale materials, we need a nanoscale probe. We probably want to be able to measure things in a magnetic field so that we can measure the susceptibility to magnetic field, the G factor. And to get the full band structure of the material, to understand this spin-orbit coupling term by mapping out that full Hamiltonian, we'd like to be able to look at the dispersion of both the filled and the empty states in the material. So how can we do that? So this is my technique of choice, scanning tunneling microscopy. And STM allows us to operate in a B field at the nanoscale and to measure empty and filled states. How does it work? We have our sample. This is a picture of an STM that was built in my lab. Oh my goodness, this STM, believe it or not, is about 12 years old. That's about as old as my son is. Pretty amazing. So our sample sits here face down in the material. This whole STM is about 1.5 inches across. The sample is inserted from above, face down. There's a sharp tip here that points up towards the sample. Here's a schematic of that, which is actually upside down, but we bring the tip in close proximity to the sample, just a few angstroms away from the sample, and then we apply a voltage between the tip and the sample. The tip is held at virtual ground, and the voltage causes current to flow between the tip and the sample. And then we measure the current, and the current is the actual experimental measurable here. So how does this work? What does this tell us? So if you look over here to the right is the way an STM works. So first I've drawn over here the density of states of the tip as a function of energy. And usually you see this sideways. So if you kind of turn your head to the right, you'll see what you would usually imagine. The density of states is filled up to the Fermi level here. And we pick our tip to be a boring material like platinum or something that has a flat density of states and cuts off sharply at the Fermi level at low temperature. And then we have our sample density of states, which is what we're actually interested in. This is what we're going to use ultimately to tell us about the electronic structure of the material. So with 0 voltage applied between tip and sample, then the Fermi levels are aligned, and there's just as much current tunneling from here to here as there is tunneling from here to here. But if we apply a voltage between the tip and the sample, we're effectively raising the Fermi level of the tip with respect to the Fermi level of the sample. And now all of these filled states here, we'll find it energetically favorable to move into these empty states here. And so the total tunneling current is going to be proportional to the number of filled states available for tunneling times the number of empty states for tunneling into. In other words, the current is going to be proportional to this rectangle times this integrated area here. And since we've chosen our tip to be boring, we can just pull this rectangle out of the integral, treat it as a constant, and the tunneling current is going to be proportional exactly to this integral under the density of states curve. And that tunneling current we measure is typically on the order of a few picoamps, which is like 10 to the 7 electrons per second. So we can use this STM in a couple of different measurement modes. We can scan the tip with respect to the sample, so we get XY resolution on the surface of the sample. And then we can also change the voltage between the tip and the sample, which gives us sort of an energy axis. So at the end of the day, we're generating a 3-dimensional data set here, where we have 2 spatial dimensions and 1 energy dimension that comes from changing the voltage between the tip and the sample. And we can look at that data in a couple of different ways. So we can park the tip at a particular XY location and change the voltage and measure the tunneling current. Here's the tunneling current as a function of voltage. This is actually the derivative of the tunneling current as a function of voltage, which gives us the density of states at a particular energy. Or we can fix the voltage between tip and sample and map the density of states over a whole area at just a single energy. And so we would get a map that looks like this. And then there's a third mode in which we operate a feedback loop, and we can get the geometrical shape of the surface by requiring a fixed tunneling current. Okay, so this tells us how we can get spatial resolution. It tells us how we can get energy resolution. But at the beginning, I said what we really want is energy versus momentum. And an STM is collecting all of the electrons that come into the tip from every which direction in the sample. So they be coming this way, they could be coming this way, they could be coming this way, and tunneling into the tip. And that is integrating out the momentum information that we want. And so we need some additional way to get a hold of this momentum information if our ultimate goal is to figure out the energy versus momentum of the material. So we have 2 ways we can do this. One way is to turn on a magnetic field. And a magnetic field quantizes the energy levels and tells us something about the dispersion. So I'm going to come back to that later. Another way is to use a technique called quasi-particle interference imaging, QPI. And in this case, electrons scatter off of a defect they scatter elastically off of a defect, and the incoming eigenstate interferes with the outgoing eigenstate, and the interference between these two eigenstates is a plane wave, a standing wave, with a wave vector equal to the difference between incoming and outgoing. And by measuring this standing wave, we can back out the incoming and outgoing momentum. So I'm going to tell you how these techniques apply to the material antimony, which is a pure element, but it's an interesting one because it's topological. And I think this is particularly interesting because antimony was actually one of the first known elements. It dates back to about 3000 BC that humans were purifying antimony and using it as eye makeup, of all things. I don't advise that. But it's, I think, really inspiring that after 5,000 years of knowing about this material, we're still discovering new things about a basic element. So for all the students here, there's a lot left to discover. So we use our STM to measure antimony. We map the topographic shape of the surface, and you can see that in this is about an 80 nanometer field of view, and there's a few single atom defects in this material. We can zoom in and we can see the clean background. These are single atoms. It has a layered structure, so we've cleaved it and we have a flat surface here. And if we look at the band structure, it's a topological material, so we expect it to fit this phenomenological Hamiltonian here. And if one does a DFT calculation of the band structure, this is roughly what it looks like. So one expects it to look like it's a conduction band, the valence band are down here. It's actually a semi-metal, not an insulator. So the Fermi level here does cross through the bulk band, so it is metallic. But if you look as a function of momentum, there's a gap everywhere. So it can still be topological. It can still have an inversion between the valence and the conduction bands. And that inversion generates these topological surface states, which is, again, these two spin-split parabolas that turn down at the edges. So this is a one-dimensional projection of the band structure here from theory. If I kind of rotate that around in two-dimensional space to see what the surface state would look like as a function of kx and ky, it looks like this beautiful six-fold symmetric flower here. Here's the inner crossed parabolas, and then the outer crossed parabolas also turn down and have these lobes here. And now I can, with my STM, measure the density of states and see how it relates. So here's some experimental data on antimony. And so here's the energy versus the density of states. Now, it's confusing because in theory land, people usually plot the energy on this axis and the momentum on this axis. And in STM land, energy is our independent variable. We're changing the tip sample voltage, and we're measuring the current. So we want to be able to compare our energy axes. So I'm just going to turn this sideways. So here's my energy axis again, and I've lined it up with a theoretical energy axis here. And I can see that indeed the features in the density of states, the peak here corresponds to a saddle point in the band structure, which makes sense. I would expect that a saddle point would have a large density of states at a single energy. And the peak here is actually kind of a cusp here, corresponds to the flat tops of these bands. So my measured density of states looks pretty good compared to the calculated density of states here. But I still want to check the momentum information. This density of states is integrating over all momenta. So here's where I'm going to use the spatial resolution of an STM. And I want to give you a couple more analogies so you really understand where this momentum information is coming from. So this is a slide. I'm going to give you a sports analogy. I like to give sports analogies for things. So when I was an undergraduate, I spent a lot of time in this boathouse. I was rowing on the crew team for Harvard, and so I spent about 4 hours a day in that boathouse. And out in front of that boathouse is a bunch of unperturbed water. Now suppose I'm an experimentalist, and I want to know something about the nature of water. So what do you do when you want to understand something? Well, you perturb it. You introduce a perturbation. And you may know, anybody who's rowed knows that it's a tradition, after you win a race, you take the coxswain, that's the little person who sits in the back of the boat and shouts at you while you row and steers the boat. The coxswain gets thrown in whenever you win a race. So there's me introducing a perturbation into the water. But what does a perturbation do? A perturbation sets up waves. right? And so if you are trying to learn about water and you introduce a perturbation, then you get this opportunity to measure the wavelength versus the velocity of the wave. And that tells you something about the nature of the water. It can tell you about the viscosity or the depth of the water. So by introducing this perturbation and getting this dispersion relation of the water, then we learn about the properties of the water. So we're going to do the same thing in our material here. We have antimony, we introduce some atomic defects, and we get waves. But instead of water waves, these are electron waves. And so we're going to use the dispersion of these electron waves, the energy versus momentum relation of these electron waves, to tell us about the nature of the material. So mapping that onto a slightly more professional context, here is a simulation, pure simulation of a material. This is an XY map, real space map of a given material. And let's suppose this material has a simple parabolic band structure. And suppose I introduce some perturbations, some defects. Now you can see in the background some electron waves scattering off of these defects. And these electron waves have a particular wavelength. And that wavelength corresponds to a wave vector, 1 over the wavelength, which is mapped along here. And the dominant scattering is going to be, so if these electrons are scattering elastically off the defects, the dominant wave vector is going to come from opposite sides of the parabola, where I have the most phase space for scattering between two sort of parallel edges of the parabola here. So all the way around the parabola, if I have a circular paraboloid here, every diameter is going to give me larger phase space for scattering. So what I should see in terms of the dominant wave vectors here is I should see a circle of wave vectors corresponding to the dominant diametric scattering around this paraboloid. So I'm going to play a little movie here where I go up in energy. So I'm going up in energy just by, theoretically, or in simulation land, applying an increasing voltage between the tip and the sample. So I'm going to move up this energy axis. And as I move up this energy axis, I expect the diameter to get larger, which means that my momentum space picture here, this ring of scattering, should get larger. Whereas in real space, the wavelength should get shorter. And so I can simulate it backwards, but then what we do in experiment is we measure the real space, we Fourier transform the real space, and we try to back out what were the original eigenstates to begin with.
How do you get positive and negative momentum from this? Because you're looking at standing waves, so it's not obvious to me how you get the...
Right, so you're absolutely right. So we're just measuring a difference between incoming and outgoing. And so it's certainly easier to solve the problem if you know roughly what the band structure should look like to begin with, and then quasi-particle interference imaging, this technique, quantifies the rough shape of the band structure. I think there are smarter ways to do it, that there should be algorithms to entirely invert the problem and get the band structure back. So far, we've been working with materials where we have a vague idea from DFT where the bands should be, and then we can quantify those bands. I don't know if that. So this is a question for Kyle or somebody else. How can we fully invert the problem to get from Q back to K? Because you're right, we're just measuring a difference vector, and what we want is the incoming and the outgoing from that difference vector.
Right. I mean, I guess maybe I'm afraid because I'm not a materials person. I don't think inverse space, right? But you've drawn something where I assume those dashed lines that's zero momentum.
Yes. Sorry, that's zero momentum.
Right, and so doesn't this, if you're just looking at standing waves, isn't always going to give you something that's symmetric? I mean, because otherwise the Fourier transform, you have to see something
complex. Well, usually
complex.
the band structure is symmetric.
Right, but you want to see something that's not symmetric, right? That's the whole. No. My original band structure is symmetric. Okay, so I see where the confusion is. So this is just a convention thing. So I've plotted the band structure here, and it looks asymmetric, but the way people plot in band structure land is they plot the high symmetry axes. So this is the 0 point, and if I actually plotted just a cut straight through along the m-axis, it would be symmetric. Or if I plotted just along the k-axis, it would be symmetric. But in condensed matter, what people do is they plot the high symmetry. So this axis is actually 30 degrees away
from this axis here, but along any one axis is symmetric. Yeah, that was a great question. Thank you, because this is so great because you forget what are the conventions that you just take for granted in your own field. Any other questions? Yeah.
So this is about the Hamiltonian. So it looks like there is a k-cube term. Typically, when there are k-cube terms in dispersion relation, you would get solitons. I mean, KdV equation kind of derives from that, and also Kp, which give solitonic solutions. I mean, I was wondering if any of that is being studied.
I don't know. I have been thinking about this only very close to the gamma point where the k-cube term is very small.
Still, I mean, if it's still, it could be some nonlinear solution
Mm-hmm.
supported by.
It's a question I haven't thought about.
But
Any other experts in the room want to jump in on that? It's a good question. Thank you. Any other questions before I move on?
You
Yeah.
really, I mean, you have terms up to very high orders because this is just an expansion in K
Mm-hmm.
of a Hamiltonian that has a lot of wiggly stuff. So I don't, I mean, similar K-cube-like terms are very common in band structures. I don't know if they, maybe it turns into a wash when you put everything else in.
Yeah, I guess. I mean, really, for everything I'm talking about, so I just included this term for completeness because it's in Liang Fu's paper, but everything that I'm talking about is really just these terms here. I'm working so close to the gamma point here. Okay, so let me play my movie here. I think it's going to play. I'm going to play. Okay, so we're increasing the energy. We're moving up the paraboloid. So our Q vector is increasing, and our real space wavelength is decreasing. So we're going to be measuring this kind of a movie, Fourier transforming it to get this, and then inverting to get the original eigenstates of the material.
And you're going to do that for different voltages? Like
Yes,
you're going to do this
exactly.
Fourier transform separately for each one?
Exactly, yeah. And I know where you're going with this. It would be
nice.
great to be able to do it holistically.
Right.
And I think that's the future. We got to get there. Okay, so for antimony, we're going to be looking at this scattering vector in particular. And because if we remember where these states came from, this would be, say, a spin-up band, whereas this one here would be a spin-down band. So we don't expect scattering between spin-up and spin-down. So we shouldn't expect cross-cone scattering. We should only expect inter-cone scattering. So this Q vector is allowed, whereas the shorter internal one here would be not allowed. So we expect that as we increase the energy from here to here, the scattering vector is going to increase, and the wavelength in real space is going to decrease. We can see the scattering off of a few defects here. So I'm going to play a movie now, and this is real data. The previous one was a simulation, but this is a data set that took about 4 days to acquire in our STM at liquid helium temperature on antimony. And this energy here, which is unfortunately not super visible, is going to start right down here at the bottom, and the movie is going to run all the way up here. And so as the movie runs, you should see the wavelength getting shorter and shorter and shorter as the wave vector gets longer and longer and longer. So those are electron waves. That's pretty cool. So, so to quantify that, we take a Fourier transform, and then we pull out the high symmetry directions, and we see some increased scattering along this trajectory here on the gamma m direction, and this trajectory here along the gamma k direction. We can fit those and pull out the largest scattering vectors. And then we can do the inversion, and we're doing it manually here. Yeah?
So do you pepper these defects on the surface, or do you have to worry about things that are buried in the bulk as well?
So this is a semi-metal, which means that the things that are in the bulk are pretty well screened from the surface. The screening length is relatively short in this material, which is actually why it's really good for testing out these techniques. But if we have tried to study materials accidentally that are too clean, and then we don't get this scattering at all. So very occasionally, we find that we have to intentionally put dirt into a material, but usually the reality is whatever we grow, it has enough dirt that we can do the technique without trying. Sometimes it has so much dirt that we can't see anything, it's all incoherent. This time we were lucky, it had just the right amount of dirt. So we can fit those wave vectors, invert, and get the original band structure. So here's the two spin split parabolas. And from that fit, we get all of the parameters in the Hamiltonian, and in particular, we get the spin-orbit coupling here. So back to our metrics, we now have a measure of the spin-orbit coupling in the material. And we can ask about our next metric, the mean free path. So what are Landau levels? And here I'm going to give you another sports analogy. So I like sports analogies for things. So as Paul mentioned, I like to run. And I like to run a lot. And I like to run in circles. So this was a race that I did a couple of years ago in Cleveland. It was actually the national championship for the 24-hour run. So the goal is you run around this loop, about a mile loop, and you run and you run and you run, and you have a chip in your shoe, and it counts every time you go over the timing mat, how many laps have you run. And the one who runs the farthest gets a prize. So I was, I like running a long way. I like this sport a lot because there are no anonymous.
I think we should
So the good thing about running is that there are no anonymous referees. It's all out there. Like whatever you do, it's all out there, and nobody can come behind your back and be like, So it's a really good balance for me because I have my share of problems with anonymous referees. I think we all do. So this is a very satisfying complement to my professional life. But I'm going to use it to teach you something about Landau levels. So even though I am a large object, and unfortunately larger since that race due to the amount of ice cream consumed in the last year, I do have a wavelength associated with me. And that wavelength, if I'm running around in a loop, has to be quantized. Because if my wavelength did not fit an integer number of times into the loop, then I would cancel myself out when I come around the other side, and that would be a bummer. So instead, if I have an integer number of wavelengths, then I can continue to exist as I run around and around this loop. And you can even calculate my wavelength, and you can calculate the quantization of my velocity, which in fact is rather small. I am not a talented runner. I am just a very stubborn runner. But nonetheless, even though my velocity quantization is rather small, it turns out that if you run long enough, you can win on stubbornness, not on talent, which is something I like. So I was really honored to have the opportunity to represent the U.S. at the World Championships in Belfast last summer, and Team USA won a gold medal in Belfast, which was pretty exciting. So I digress, and I'm going to come back to electrons, which are also quantized as they go in loops, and they are quantized with an energy spacing that is much larger because the electrons are smaller, they're less massive, and they go faster. And so this energy quantization is actually something that we can measure with our instrument. So this is the density of states as a function of energy. Again, you've seen this before. And this is in zero field. And now I'm going to turn on a magnetic field, which gives this quantization condition. When I turn on magnetic field, I see that the energy levels are quantized with a spacing here of a few millielectron volts. And from the sharpness of those energy levels, which I've measured here, here's the sharpness of the energy levels, I can take the inverse of the Landau level width, and that gives me a lifetime, and the lifetime gives me a mean free path of 60 nanometers. So from the quasi-particle interference, I get the spin-orbit coupling. From the sharpness of the Landau levels, I get the mean free path. And then I can also get the G factor by looking at the Landau levels in a different energy regime down here near the bottom. You can derive the formula for the energies of the Landau levels and note that the G factor is here. And so we can fit the energy of the bottom Landau level as a function of magnetic field. Here the Landau levels as a function of field. By fitting those energies as a function of field, we can back out a G factor of about 12. which is not so large for this material, but it's larger than a free electron. Okay, so this has given us a way with STM to measure these metrics for spintronics devices. And so this is a way that we can quantify future topological materials. It turns out that antimony, because it's a semi-metal, is not so useful for the spintronics application, because I'm going to skip through this. We have some defects in this material. They look like the Lorax. So having measured these metrics for spintronics in antimony, I want to point out that antimony is not the best material for spintronics or for some of the other applications of topology, because the bulk conduction shorts out the interesting properties of the surface state. But it was a good playground for understanding those properties. So spintronics is one application of topological insulators, but the weakly correlated, the first generation topological insulators, even if they're not semimetals, even bismuth selenide, bismuth telluride, some of the other first generation weakly correlated topological materials, they tend to have impurities and a conducting bulk just from the impurities, even if they're nominally insulators. We can get some more interesting applications of topological materials in topological quantum computing, and I understand you heard from Professor Kane yesterday about this, and so I'm not going to compete with him in trying to explain topological quantum computing. But I will say that you can do a lot more interesting things with topological materials if there are strongly correlated ground states. If the strongly correlated ground states can lead to degeneracy and non-local behavior, non-abelian statistics. On the other hand, strongly correlated materials are a lot harder to calculate. So in my antimony story, I started with a DFT band structure. And it turned out that my measured band structure looked pretty much like the theoretical band structure. But in the world of strongly correlated materials, we don't yet have computational techniques for the band structure. We have some kludges, but there are human tunable parameters that we have to subjectively choose in order to compute a band structure. So for the strongly correlated materials, it's really kind of a brave new world where experimentalists can resume the lead. I think that one of the exciting things for theorists in the field of topological materials is that these weakly correlated materials, the theory led the experiment. So theory predicted experiment found, theory predicted experiment found, in that order. And now in the world of strongly correlated topological materials, this is a place where I think experimentalists can really start with an exploration and then tell the theorists what we're seeing. Okay, so there's a couple of beautiful review papers out there. This is one by Leon Balance that shows that here you have the spin-orbit coupling axis, which makes things topological. And then if you turn on electron correlations, how much electrons are talking to each other, then you can get some really interesting phases of material out here. But these are all highly speculative. And so we as experimentalists want to explore this space and tell the theorists what's really there. So I'm going to talk about a material called samarium hexaboride, which has been known since the 70s. And it has this kind of unusual resistance versus temperature plot. So as we lower the temperature, the resistance increases. So it's a resistor. But then as we get down to about 4 or 5 Kelvin, the resistance plateaus. And that is not the behavior of a normal insulator. That is really bizarre. Most insulators, the resistance would continue to go up and up and up as you go to lower and lower temperature. And so this plateau has caused almost fistfights for about 40 years now. Some people think it's impurities in the material, and various exotic solutions have been proposed, but there's been little agreement about what this plateau actually is. And then it was proposed by, let me talk about the insulating state first. So the part that we understand, the insulating state here, where the resistance is starting to rise, is happening because this is a Kondo insulator. So it's a different kind of insulator. It's not a band insulator like I showed at first. It's a strongly correlated insulator. So if you put a single magnetic impurity into gold, gold itself, this orange curve here, is a metal. Its resistance goes down as you decrease the temperature. But if you start to put magnetic impurities in, then the resistance pops back up again at the lowest temperature. And the resistance is popping back up because at low temperatures, this single magnetic atom attracts a screening cloud of electrons around it, and so it becomes a larger scattering center for the conduction electrons in the material. The conduction electrons come, they see the spin, they say, I'm going to screen for a while, they hang out, and they don't, and they get extra resistance. But if you have a material like samarium hexaboride, where every single samarium is acting like one of these magnetic impurities, then you have a Kondo lattice, like this. So every single samarium is getting a screening cloud. And that effectively increases the resistivity of the material. It opens up a gap in the density of states as the conduction electrons hybridize with the F electrons that are localized on the samarium. And that is what increases the resistance as the temperature is decreased. So now if we turn to this plateau at low temperature, what was predicted in 2010 by Pierce Coleman and collaborators was that this plateau is actually a surface state, a topological surface state. And so what happens is as the resistance rises and rises and rises, at some point this topological surface state begins to short out the bulk resistivity. And it's been shown experimentally very clearly by physically taking a sample and thinning it down and thinning it down and thinning it down and looking at the ratio of this plateau to the rest of the resistivity, that this plateau actually is a surface state. But is it a topological surface state? So in order to understand whether it's a topological surface state, we want to measure the band structure again. We want to know what's the dispersion of those electrons. Okay. So let me start back at high temperature, and show you experimentally what we know from STM about this material. So at high temperature, what we expect in a cartoon form, so this is theory, this is not STM, we expect that there's a conduction band of d electrons, and there's the F states of the samarium near the Fermi level, and at high temperature they're not talking to each other. This conduction band is happily conducting, and we have a pretty good metal with low resistance up here. And then as we lower the temperature, so let me zoom in. This is a large energy scale of 4 electron volts here. But I'm going to zoom in on the Fermi level, and I see that these F states, there's actually a couple of F states that are closely spaced. I'm zoomed in about a factor of 100 here. So there's the Fermi level again. The conduction band has now become so stretched out that all you see is the 2 vertical lines here. And the F states are crossing it. So I'm still at high T. The conduction band is not bothered by the F states. But if I lower the T, then the conduction band starts to see the F states, starts to congregate and try to screen those F states. So when the D band starts interacting with the F states, they hybridize and open a gap in the density of states around the Fermi level. And that gap is what makes it an insulator. And so the interesting thing here is that you see that now the F state has popped above the D state. So that starts to look like a topological insulator. It's that band inversion that we need for the interior to have this topological twist in the band structure. But I simplified a little bit because this is just a cut along one axis of the material. So it's a, well, I should have said it's a one-dimensional cut. This is the one-dimensional cut that tells me at one location in momentum space there's a band inversion. And in fact, for a material to be topological, you need to look in the full 3-dimensional momentum space, and you need an odd number of band inversions. So in order to really understand this, I need to look in 3 dimensions. So here's a 3-dimensional momentum structure of the material. And there's actually 3 sets of Fermi surface crossings at 3 high symmetry points in the Brillouin zone. So this is Kx, Ky, Kz. And here are my Fermi surfaces. And so this D band that I showed here, crossing this Fermi surface, it actually comes from just a cut along one of these 3 pockets in the full 3-dimensional momentum space. And so what I see here theoretically, or in a kind of cartoon form, is that there should be 3 band crossings at these 3 high symmetry points. 3 is an odd number, so it should be topological, and there should be a surface state spanning this band gap around the Fermi level. So if I take a little closer look, I see that these Fermi pockets are actually footballs, not soccer balls, or rugby balls rather than footballs, depending on what country you're in. And it's meaning they're oblong. So the surface projection of these is going to be different. This one is going to project to a narrow pocket of the surface, and this one is going to project up to a fatter pocket at the surface. And so if I just kind of take a cut along this line here, and I look at the filled bands, here's the Fermi level, and these are the empty bands, I would expect two different kinds of surface states. I would expect steeper ones for the skinny bands, and shallower ones, or heavier ones, for the wider pockets. So we're going to use our STM to understand this. We scan the surface of samarium hexaboride, cleave it, expose a clean surface, and we scan the surface. We have just the right number of defects here, and we can do spectroscopy. We can look at our full three-dimensional data set here where we measure the energy and then the X and the Y momentum. We employ the quasi-particle interference imaging technique, so we Fourier transform the real space, and we can look at the peaks in momentum space and how they disperse as a function of energy. Here's the energy axis. And if we look at the energies away from the gap, these are our data points here, which fit pretty well to the cartoon band structure. And so the real question is, what's going on inside the gap? And this is the unknown. And this is something that has been really hard to figure out from techniques such as ARPES, which is generally the powerhouse technique for understanding new topological materials. But in this case, the energy scales are so small, and so much of the interesting physics is in the empty states up here that it's been really hard for ARPES to tease apart this problem. So we use STM. We look at the energies within the Fermi level. So where are my energies here? I think, oh, here they are. This is from 8 millielectron volts down to 1 millielectron volts. This is a very small energy scale and above the Fermi level. And we can see some dispersing peaks that look like the top of a Dirac cone. And now I'm going to go to energies that are just below the Fermi level. So from -2, or 2, 0, -2, down to -8 millielectron volts. And I can see that there's a peak that's dispersing in and dispersing out again. And if I plot that versus energy, I get a full Dirac cone sitting inside the band gap of the material. Okay, so putting this all together, we expected a steeper Dirac cone and a shallower Dirac cone, and that is indeed what we find. And in fact, if we look at the slope of this shallower Dirac cone, it corresponds to an effective electron mass of about 400 masses of the electron, which is the heaviest known Dirac state ever seen. And what that means is that there's really a lot of states near the Fermi level. So this is a very sensitively tunable material, and it's exciting to see what can happen with these states as we start to play around with this material more. So I'm going to skip the ARPES business, and I'm going to skip a bunch of stuff here, and you can ask questions if you want. And I just want to show you very briefly some fun stuff that we're doing. Oh, this is fun. My students sent me this email last spring. They figured out how to manipulate atoms on topological materials. So one of the fun things that we're trying to do now is manipulate atoms, magnetic atoms on the surface, and create the scattering sites. So now we should be able to channel topological surface states by putting up rows of magnetic atoms to kind of keep those surface states scattering off of the edges but moving along in a channel. We're hoping that this will get us some funding. We tried hard to impress the folks over in California.
So that electron probably can decay, right? That electron is, you said 400 times an electron?
Yes, it has a very, very short mean-free path. You're absolutely right. So I have some...
Because of the solid state phonons and all that stuff, or...
Well, no, it's just, it's exactly as you said. It has a very, it's very heavy. So that means that in a very narrow energy range, there's a lot of states available to scatter over a wide range of momentum. And so it's the wide range of momentum available corresponds to a very short real space distance. So here.
I was
Sorry, I
thinking
ran
more
right
like I'm a particle physicist, more
Okay.
like particle physics decay, because that's not the lightest charged particle. And for instance, pion is
Mhm.
now lighter than that electron. So
Yeah.
probably that electron can decay pion, neutrino, or something. It will be some lifetime for it from that perspective.
This is a really interesting question. I never thought about it in
But
those
in
terms.
particle physics, there are heavier Dirac particles. The tau lepton, for example,
Yes.
is 1800 eV or something like
Oh, sure, yeah. So this short lifetime is I've always thought about it for a completely different reason, but I never considered this question. So, I mean, there must be some kind of fundamental thing we can say, because we can look at the, so these are the defects that are doing the scattering. So we Fourier transform this whole field of view. Here's the Dirac state, and then we just take the scattering signature, and we mask out everything else and inverse Fourier transform just the scattering signature of the Dirac cone. And when we do that and superimpose it, we get that these are the places where the scattering is happening. So this is basically saying that the mean free path is really short. This is 80 nanometers, and the mean free path here is like 5 nanometers. So I think you're onto something, but I don't know how to crisply formulate it yet. But it's a really interesting point. The decay mechanisms are quite different than in particle physics, but I think you're onto something. Okay, I know I'm done, but I want to show you some really cool stuff that I have a few high school students and undergraduates working on. So just this last year, we started working on topological metamaterials. So it turns out that this kind of physics, this topological physics, can happen not just in the quantum electron band structure, but it can happen in the acoustic band structure of a material. So you can look at a material and you can say, what is the frequency of sound as a function of the wavelength of sound? And so you can make a classical analog of a quantum topological material by inverting bands, by inverting acoustic bands. And so what we did is, so we built a material that looks kind of like this. It's a honeycomb lattice of stainless steel pillars in air or water. And it turns out that you can calculate the band structure as a function of, so this R is the radius of the pillars, assuming a 1 meter lattice constant, which is ridiculous, of course. But I'll get to some more realistic parameters in a moment. This was a high school student who wandered into my office during his junior year and said, I'm a topologist. What can I do in your lab? And I said, okay, well, we'll figure out something for you. So he did some simulations of this honeycomb lattice and found that as he tuned the radius of the pillars, he found that these phonon bands, or these acoustic bands, inverted. They reached an accidental degeneracy point, and then they inverted. So now, over here, we have the state with fewer nodes in the wave is actually above the state with more nodes. And so that corresponds to a topological phase transition between a denser array of pillars and a less dense array of pillars. So we did some simulations and tried to make a waveguide where on one side we have a dense array of pillars and on the other side we have a less dense array of pillars. And so at the boundary there should be an acoustic state that propagates, even though these two sides can both have a gap that's insulating, that doesn't allow acoustic propagation. So I just want to show you one really cool movie. So this is a Schlieren optics setup. This whole thing is about a foot across, and we send a sound wave in one side, and the sound wave rarefies and compresses the air, so it causes minute changes in the index of refraction of the air. And then we use a strobe light at 28 kilohertz to diffract off of this essentially new diffraction grating from the sound wave that's propagating. And oops, how do I do this? I'm going to play this movie. How do I make this movie play? So you're optically seeing sound waves here by strobe. Somebody's doing it with a cell phone, so that's why it's wiggling around. But So those are actual sound waves that are propagating, strobed at 28 kilohertz, or ultrasound waves. And then I have this undergrad here who's built this thing, and he hacked a 3D printer, took it apart, and put a microphone on where the inkjet should be. And now he wrote assembly code to force it to scan in the direction that he wanted it to scan in. And he put the topological waveguide here between the denser lattice and the less dense lattice. So first we did the control experiment with no waveguide here. We had a microphone, or sorry, a speaker here, and you can see the waves go everywhere. And this is data that's 2 days old, and we haven't optimized this at all. And then he put the waveguide, so here's the waveguide, and you can see that it's preferentially starting to propagate. So we have a lot of work to do, but I think this is really cool because these are high school students and undergraduates who are doing these experiments, and there's a huge phase space of new materials that we can look at now, and hopefully try to use these to get a better physical understanding of what's going on in quantum land. So I thank you very much for your attention and your indulgence in the last few minutes. There were good questions during the talk, so
There were
it's
questions
okay.
during the talk. Let me turn the lights on. Just up. Very good.
Can I ask? It's a technical question. Slightly less obnoxious than why would you run in a loop for a day? But maybe. So you're.
No anonymous referees.
Yes.
Okay.
Well, so when you do this conductivity versus position, and you're scanning for 4 days, I assume you sit in one spot and you measure the conductivity versus voltage, and then you move. You don't repeat the.
That's right.
Yeah. But even so, it seems really impressive that over 4 days you can kind of avoid angstrom level drift.
Yeah,
Is there
so
some
over
other
4
feedback?
days, we typically do have a drift of a couple of angstroms, but we can correct that in software after the fact because we are simultaneously measuring the atomic lattice, and we know what the atomic lattice should be. It should be perfectly periodic. So we do a kind of a spatial lock-in amplifier technique. So we multiply the known atomic periodicity times the measured periodicity and lock in to the measured frequency and say, well, that's
So as
wrong
long
by a little bit, and we shift it back to the frequency it should be.
So as long as the drift
As long
rate
as
is
the
small
drift
compared
is-
to the sampling time over the
Exactly.
interim spatial
Yeah,
unit.
exactly. And we do still have to work pretty hard to get it to be that small. We don't have to be perfect.
This question about the self-energy and how the scattering's happening is kind of neat, especially because ARPIS can't really see this. I guess these states, ARPIS thinks these states start to exist beneath 100 Kelvin, and there's a lot of electronic disorder at 100 Kelvin. But when you get down to 4.5, maybe KBT is really small compared to the band gap, so the electronic disorder kind of all largely freezes out. Do you have any way of seeing if self-energy is changing a great deal as a function of temperature or of evaluating that particular?
Yeah, we have, I think I have a hidden slide for that. So we've done some really careful fits, and you can see that the lifetime is changing quite a bit as a function of temperature here. But we, in our particular system, we're just, for technical reasons, are limited to 50 Kelvin, so we can't go all the way up to 100 Kelvin. Otherwise our piezo's would short out.
Any others? Then I think we should go down for refreshments.
Okay. Thank you.